Have you ever just looked around and wondered what stops everything from just, falling apart? I mean, what holds your desk together, your phone, what holds you together? Well, the answer is this incredible invisible force. It's a fundamental drive that shapes literally everything around us, and it's all about chemical bonds. So let's dive in and figure out how they work.
Right, so the short answer is chemical bonds. These are the connections, the little bits of glue between atoms that make up all matter. But why? Why do atoms even bother connecting in the first place? What's the deal? What do they get out of it?
And here it is, the core idea. Atoms aren't just bumping around randomly. Nope. They're on a constant, relentless quest for one thing: stability. Think about it like rolling a ball down a hill. That ball naturally rolls down, releasing energy to get to the lowest, most stable spot at the bottom. Atoms do the exact same thing, and forming bonds is how they roll down that hill. Okay, so let's get into this motivation. Why is being a lone atom so unstable for most of them? And how do they go about fixing that problem? A single unbonded atom is kind of like a person who's had way too much coffee. It's jittery, it's buzzing with high energy, it's totally unstable. To calm down, to find its zen, it has to form a bond with another atom. That process releases all that pent-up energy, and the new molecule that's formed is always more stable than the two separate atoms were on their own. So, how does an atom know how many bonds it needs to make? That's where this idea of valency comes in. You can think of it as an atom's, its social need. It's all about filling up its outermost shell of electrons to feel complete and stable. For an atom like carbon, that means it wants to form 4 bonds. For hydrogen, it's happy with just 1.
All right, so atoms need to bond. The first strategy they use is a pretty cooperative one. Let's call it the covalent sharing club.
So here's how this club works. You've got 2 atoms, usually nonmetals, and they get close enough to notice each other's unpaired electrons. They decide to overlap their outer shells and share a pair of those electrons. Now each atom kind of feels like its outer shell is full. This sharing creates a really stable partnership. That's the covalent bond. And in the process, they release all that unstable energy and just chill out.
But, sharing isn't always perfectly equal. Some atoms are way more greedy for electrons than others. This greediness is called electronegativity. It's basically a measure of how hard an atom pulls on those shared electrons. When one atom pulls the electrons closer to itself, you get a polar bond. One end becomes a little bit negative, and the other becomes a little bit positive. And this little imbalance is a huge deal. It's why water behaves the way it does.
Now for a totally different strategy. If covalent bonding is a friendly partnership, this next one is, it's more like a dramatic giveaway followed by a powerful, irresistible attraction. Welcome to the Ionic solution. You've got a metal atom with a couple of extra electrons it doesn't really want, and then you have a non-metal atom that desperately needs those electrons to feel complete. So the metal just says, "Here, take them." It completely transfers the electrons over. The metal becomes a positive ion, the non-metal becomes a negative ion, and bam! Opposites attract. They lock together in this super strong, super organized crystal structure called a giant ionic lattice.
Sharing versus transferring. Think about it. These two pretty simple atomic strategies end up creating materials with wildly, completely different properties. Let's see how that plays out.
So here's the big takeaway. These two paths create fundamentally different kinds of structures. Covalent bonds tend to form individual, discrete molecules, like little water molecules floating around. But ionic bonding, that creates these huge, highly ordered crystal lattices. This one difference in structure is the entire reason a diamond is nothing like a salt crystal. And this shows you the sheer power of a covalent network. In a diamond, every single carbon atom is locked to 4 others in this unbreakable 3D fortress. If you want to melt it, you have to break every single one of those incredibly strong bonds. That's why its melting point is just ridiculous. It doesn't even melt, it just turns straight into a gas at around 4,000 degrees Celsius. And that structure also explains why it's one of the hardest substances on Earth and doesn't conduct electricity at all.
But what about stuff made of simple molecules, like water or methane? Okay, the covalent bonds inside those molecules are super strong, sure, but that's not what determines if it's a liquid or a gas. What really matters are the very weak forces of attraction between the separate molecules. So when you boil water, you're not breaking the strong bonds inside the H2O. You're just overcoming the weak, sticky forces between neighboring water molecules, and that takes way less energy.
All right, let's bring this all home. We're going to wrap up by looking at how these simple bonding rules explain some very familiar things about the world we live in.
So, here's a classic chemistry question for you. We all know metals conduct electricity, right? But what about an ionic compound, like regular table salt?
When it's a solid crystal? Absolutely not. No way. The positive and negative ions are all there, but they're locked rigidly into that crystal lattice. They can't go anywhere. And since electricity is just the flow of charge, if nothing can move, solid salt is a great insulator.
But if you heat that salt up and melt it, the whole story changes. You pump in enough energy to break that lattice apart, and suddenly those ions are free to move around. And because they're charged, their movement is an electrical current. So the key word here is mobility. If you don't have mobile charges, you don't have conductivity. Simple as that.
So what about dissolving something like salt in water? Well, you can think of this as another kind of battle, an energy war. When you drop salt into water, the polar water molecules swarm around the ions. If the attraction between the water and the ions is stronger than the attraction holding the ions together, the lattice gets pulled apart and the salt dissolves.
But sometimes that ionic bond is just too tough. A great example is magnesium oxide. The attraction between the doubly charged magnesium and oxide ions is immense. Water molecules come in and they pull, but they just aren't strong enough to break that lattice apart. It's an amazing example of the ionic bond just flat out winning that energy war.
And for molecules, it all comes down to a really simple rule you might have heard: like dissolves like. Polar things, like sugar, dissolve really well in polar water because they can form similar kinds of strong attractions. But nonpolar stuff, like oil, it won't dissolve in water because it just can't form those strong connections. It's just not worth the energy for water to break its own powerful bonds to let the oil in. So, there you have it. From the hardness of a diamond to why salt disappears in your soup, it all comes back to one fundamental thing: the relentless drive for atomic stability. These basic rules of sharing and transferring electrons literally build our entire world, which leaves us with a pretty cool final thought. If we understand these rules so well, what new materials, what new realities can we start to engineer just by playing with these bonds?